In this video, we'll look to define 8 different circle theorems and how they can be used to find and give reasons for missing angles. I would recommend before you start watching this video that you review the angle foundations and the polygons video. Many of the points raised in those will come up in this video and be used in the answers. Let's look at the circle theorems in turn. Firstly, the angle at the centre of a circle is twice the angle at the circumference of a circle, within the same arc. This means that if angle A was to be measured at 35 degrees, the angle at the centre, or 2A, would be 2 times 35, which would give you 70 degrees. Next, we have the angle formed in a semicircle is always a right angle. This means that any triangle that has the diameter as the longest side and the opposite angle touching the circumference, then that angle will be a right angle. Next, we have the fact that angles from the same arc in the same segment are equal. With two lines crossing, the angles that are vertically opposite will always be equal. As the ends of the lines are limited by the circumference of the circle, this creates similar triangles, which therefore have the same internal angles. So A will equal A and B will equal B. This fourth theorem states that the opposite angles of a cyclic quadrilateral add to 180. This means a four-sided shape within the circle. So in this example, A plus C will equal 180 and B plus D will equal 180. In the next theorem, it's shown that the perpendicular line from the centre of a circle to a chord will bisect the chord. So if the chord crosses the radius at a right angle, the two sides of the chord will be equal. By extension, if that chord continued to the outside of the circle, then it follows that the angle between the tangent and the radius at the point where the tangent touches the circle is also going to be a right angle. If we extend this further, we can state that two tangents drawn from a point to a circle are going to be equal. We can find that this forms a kite shape, and we can use the properties of a kite in that the longer sides are going to be equal in length, as are the shorter sides, as they're both radiuses. Lastly, we have that the angle between a tangent and a chord is equal to the angle at the circumference in the alternate segment. In effect, the angle formed between a triangle inside the circle and the tangent outside is the same as the opposite angle inside the circle. Let's see how these can be used in some exam-style questions. Here, we're told that A, B and C are points on the circumference of a circle with a centre of O. DAE is the tangent to the circle at A. Angle BAE is 53 degrees and angle CBO is 38 degrees. We need to work out the size of angle CAO. When they say you must show your working, it's another way to say give reasons for all your answers and the numbers that you're using. In order to work out the size of angle CAO, we could proceed in several different ways. I would always suggest starting with looking at the information that they're giving you in the actual question. As is a triangle within a circle, which also has a tangent and a radius, we'll probably use the fact that the angle between the radius and the tangent will be 90 degrees, and the alternate segment theorem for the triangle. So let's start by using the fact that the angle between OAE is 90 degrees. If we subtract 53, we'll get 37 degrees, which is the angle at OBA. As triangle BOA is isoscelean, as it can be made of two radii, we can say that the angle at OBA will also be 37 degrees, as they're both the base angles of this isosceles triangle and therefore equal. If we add this to 38, we'll get 75 degrees as the angle of ABC of the triangle. This will match the angle at CAD due to the alternate segment theorem. If we know that the angle at OAD is 90 degrees due to it being the angle between the radius and a tangent, then CAO will equal 90, take away 75 degrees and equal 15 degrees. So we can state that CAO equals 15 degrees. We've also stated our reasoning throughout the working out for these problems. Here we have a problem where A, B, C and D are points on the circumference of a circle with a centre of O. FTE is a tangent to the circle, and we must show that y take away x equals 90 degrees. We're also asked to give a reason for each stage of our working. We can see that BDE will equal y degrees, as it's the alternate segment to BAD. We also know that ODE will equal 90 degrees, as it's the angle between the radius and the tangent. If we subtract ODE from BDE, we'll be left with x degrees, so we could say that y take away 90 equals x degrees. If we then add 90 to both sides and subtract x from both sides, we'll get y take away x equals 90 degrees. So we've just shown that 90 equals y minus x, as per the question, and again we've shown our reasoning throughout the answer. Let's have a look at another one. In this question, we're told that A and B are points on the circumference of a circle, centre O. AT is a tangent to the circle. Angle TAB is 58 degrees and angle BTA is 41 degrees. We're asked to calculate the size of angle OBT, and we're asked to give a reason for each stage of our working. We know that OAT will be 90 degrees, as it's the angle at the radius and a tangent. OAB will equal 90 minus 58 degrees to give us 32 degrees. As this will form an isosceles triangle due to the two sides of the triangle being radiuses, we can say that OBA must also be 32 degrees, as those are the base angles of the isosceles triangle. ABT forms a triangle, so we can subtract 58 and 41 from 180, because angles in a triangle equal 180, to get the angle at ABT to equal 81. OBT will equal 81 plus 32 to give us 113. So the size of the angle OBT is 113. In this video, we defined the 8 circle theorems and then used them to solve the questions regarding the missing angles. In the next video, we'll be looking at how to go about presenting data in two-way tables, bar charts and pie charts. I'll see you then.